Welcome students. We want to discuss about double integrals over rectangles today. Before we start, I want to go with the quote of Albert Einstein. He doesn't need an introduction. So don't worry about your difficulties in mathematics. I can assure you mine are greater. Okay, that's Einstein. Uh, so let's proceed with this double integral over rectangle. So let's start with going to what we already are aware of. By starting to compute area of the region that lies below the line segment 0, 2 and above the parabola 16 minus x squared. So we start with so this is your parabola 16 minus x squared. It's not for scaling, and you want to compute the area, which is the area here. This is the area we are interested in. We are interested in this area below the curve from 0 to 2, right? So how did we go about it? If you recall, and I want to basically connect that idea with a to b, and I have f of x, and I want to find out the area below this curve. So what you did was the following. You did compute delta x, which was b minus a over n. So you divide this into small rectangles by first dividing 0, 2 into small line segments, and between here you choose any. So this will be x1 star, then you choose x2 star, and so on. So let's see. So in this case, if this is x2 star, you basically go and make x2 star as a height, f of x2 star as a height approximation over this rectangle. And then you find out this area, and then you add it up among all. So the idea is, if I want to generalize this, delta x be b minus a over n, and then I'm looking at f of xi star delta x, because the width, the bottom width is delta x. So this width is delta x. And then I'm essentially finding the area of this, which is f of xi star delta x. And then I sum all this area up. So if there are n subdivisions, I'm going to add them up. I'm going from 1 to n. And then, of course, this will be a coarse approximation. This will not be an accurate approximation. So what we do is we take the limit as n goes to infinity, and we got the area below the curve above x-axis. So this was a case in one dimension, right? One dimension or function of one variable. Now we want to generalize the same scenario to function of two variables. Essentially, the idea remains the same. However, here we have z equals to f of xy. Our domain is 0, 2 cross 0, 2. So we have, this is our domain, 0, 2 cross 0, 2. And we want to, so consider the part of function on top of this, which is given by this green, piece of surface. So this surface here, and you want to find out what is the volume. So this is your green surface here, just coloring it up. Yeah, so this is the green surface we are interested in, and we want to find out the volume of the solid which is formed by having this green surface on the roof and these as the side wall. So these are the side walls of it. Yeah. So what is the volume of this three-dimensional object and how do we find it? So again, the idea would be the same. Instead of now making rectangles like in the function of one variable, in function of two variables, because we are finding volumes, we'll make rectangular parallelopiped. Yeah. So the way we go about it is the following. Suppose your region, we still go back to z equals to 16 minus x square minus 2y square. We will divide 0, 2 cross 0, 2 into 4 rectangles. So instead of intervals like here, we will have our domain will be divided into rectangles like here. So we divide our domain into rectangles, and so these are the rectangles we get. So let me just sketch the rectangles. So these are the rectangles we get. And we have these rectangles. And then we choose any random points here to give us the height. But in this example, we are choosing that point to be, so for first rectangle here, we are choosing this point to give us the height. So if we choose that to give us the height, we choose this point to give us the height, we get the following. A rectangular parallelepiped, and volume of this would be, suppose I choose, so it will be f of f of f of xi. So in this case, let me call this point as x1. So the x will be, let's call this as x1, and this point be y1. So this point will correspond to x1, y1. So we are taking x1, y1 times, what is the width of this guy? This is going to be area of this rectangle, which is going to be delta x times delta y, right? So this will give me the whole volume of this solid. Yeah. Then I basically go for the other point. I get, draw with a different color pen now. So I get the second solid is this one here. Again, this is obtained by, if I call this point, so let me label these points properly. So this one would be x1, x2. This corresponds to the back one, or here also we have on this part, we have y1, we have y2 here. y2 is this point, y1 is this point here. So how will the area look like? So each of this, we are calling this length, because we are dividing it equally, let's call this as delta y, delta y. This part is going to be delta x, delta x. Now what is the volume of the second one? So about this piece, what is the volume of this guy? The volume of this part is going to be, so plus f of, now this point was used for the first part. Sorry, this point was used for this one we had x1, y1. Now we are concentrating on this top of this rectangle. In that case, we have, you see the height is given by this point here. So what is the volume of this rectangular parallelopiped is given by f of, again, x2, y1. So that is for the height, and the area of rectangle at the bottom is same, delta x, delta y. Similarly, about this point, what about this guy here? So in this case, we have x2, y2. So we have this rectangle will be given by f of x2, y2, delta x, delta y. And for the third one, we get this rectangular parallelepiped, where the height is given by f of x1, y2, delta x, delta y. So when you add, you get some of these some of the volumes of this four rectangular parallelepiped, although this is a very coarse approximation, as you can see. However, something interesting happens if you increase the number of rectangles you're creating. So suppose if you have 4 by 4, then you get to this. If you do 8 by 8 rectangles for the domain, then you get to this. And if you do 16 by 16, you get to this. Now this already starts looking like this, right? So the more number of rectangles you create, the better approximation you get. So you are looking at, so this was what is called as one-dimensional Riemann sum. And here we are still looking at Riemann sum, but we can call it so-called, we can give it, say, two-dimensional Riemann sum. Okay, so let's proceed with this. So let's formalize what we have learned now. So suppose f is a continuous function defined over rectangle R equals to AB cross CD. That means what? What does this rectangle means? That your x is between AB and y is between CD. Then we define, so to create these rectangles, we'll define what is called partition of R. So what is the partition of R? So partition of R into sub-rectangles is rectangles of form R11, R12, Rmn, which are given by the following. So we have A gives me x0. So A, B is partitioned into m parts, equal parts, each of which is of width, what each of it width is delta x, which is b minus a over n. Similarly, your y is divided from c to d, and we divide into n parts, and each of it has width delta y, which is d minus c over n. So we get delta x equals to this, delta y equals to this, and xi is a plus I delta x, yi is j plus delta j. So if you look at the diagram, this is what is happening. We divide a to b into m parts, and we divide c to d in n parts, and this gives rise. So if you look at this one here, this gives me a rectangle. So I get sub-rectangles here, right? So I get sub-rectangles. Now I'm basically choosing in each rectangle, I'm choosing a point at random, which is basically given by the following. So suppose I look at Rij rectangle. Rij is formed by the following. So we get Rij is formed by xi xj. So I'm looking at xi xj and yi yj. So I'm looking at this, I get this rectangle, and I'm choosing any point in random, at random, xij star, yij star. And when we take this point, we basically use the value of function at that point for the height. And once we get that height, we basically make a rectangular parallelepiped out of it. and volume of this parallelopiped is given by f of xi star y xi j star yi j star. So this gives me the height, and the area of base is delta x times delta y, which I'll call delta A. So this is an approximation. And as you saw in this example, the more number of subdivisions you take, the better approximation you get. So we'll let the limit as n goes to infinity. In this case, we get our double integral over region R f of x, y, dA. So this is a notation for it. And of course, provided that this limit exists, we will have the integral. Continuity has to play an important role in this uh, for such a limit to exist. Okay, so this is the definition of double integral. Now note that if f of xy is greater than or equal to 0, for all xy in the domain, you get the volume under the surface. But in our definition here, we are not said that we have not nowhere said that f of xy has to be greater than or equal to 0. So this defines a general double integral over rectangle R. So this is very similar to the idea of Riemann sum. However, here n goes to infinity. In this case, we will have both m and n both go to infinity. So we are summing these over all rectangles. So for every rectangle, we sum this volume of the corresponding rectangular parallelopiped, and we add all of them up. So this gives us the concept of double Riemann sum. Okay. So now let's work it out with an example. Estimate the volume of the solid that lies above the square R 02 cross 02 and below the elliptic paraboloid. So this is the same elliptic paraboloid we are talking about, z equals to 16 minus x squared minus 2y squared. And we are asking, use the partition of R into 4 equal squares and choose xi, j, yi, to be the center of this. So let's draw this. So I'm going to draw the domain in this case. The domain is basically a rectangle. 02 cross 02. So 02 cross 02. So 02 cross 02. And now I'm dividing into 4 parts. So I'm dividing into 4 equal squares, and I'm choosing my, so this is going to be my x1, y1. This is my, so I'm choosing this as a midpoint. So I'm going to use star, but instead of that, I'm going using bar, which indicates a midpoint. This is going to be x2, y1 bar. Then I have x1, y2 bar, and this point will be the midpoint of this guy, which is going to be x, so x2, y2 bar. So what are these points? So these points are, this point is midpoint of this rectangle, sorry, this square. So this point is simply 0.5, comma 0.5. So approximate volume is f of x1 bar, y1 bar, delta x, or delta A. Because we are dividing into equal parts, I'm going to use delta A for all of them. And what is my delta A? delta A is, what is the area of this, each of these? So this is 1, this is 1. So delta X times delta Y, which is going to be 1 times 1, which is 1. So let me write that down. So approximate volume is this, f of x1, y1, x1 bar, y2 bar plus f of x2 bar, y1 bar times delta A, delta A. So each of this is a volume of the corresponding object, f of x2 bar, y2 bar, delta A. So this is my volume. And if I have to compute this, this is going to be f of x1, y1. So it's midpoint of this. This is going to be f of 1 by 2, comma 1 by 2, delta A, which is 1, plus f of, this is 0.5, so 1 by 2 again. What about y2 bar? Y2 bar is a midpoint of this, so this is going to be 1.5. So your y coordinate is 3 by 2, 3 by 2. So we have f of 3 by 2, 3 by 2 times 1, delta is 1. Then we have f of x2, which is 3 by 2, then y1 bar is 1 by 2 times 1, and then we have f of x2. So we have x1 y2, x1 y2 would have been 1 by 2, and then here we have 3 by 2 comma 3 by 2 times 1. And if you simplify this, so this is going to be 16 times half square minus 2 times half square plus 16 minus half square minus 3 by 2 square plus 16 times 16 minus 3 by 2 square. So, well, it's 2 times y square, right? So 2 times this minus 2 times 1 minus 2 square. And then next one is going to be 16 minus 3 by 2 square minus 2 times 3 by 2 square. And then when you add all of them, you get actually the answer is 49. So this is an approximation of the volume. But the key idea is essentially you are, if you look at this one here, this expression, you are taking summation j going from 1 to 2 of f of x1 y j delta a, and then you are summing then what? Then you have f of x2 yj delta a and summation again j going from 1 to 2. And if you want to write it as one sum, you are writing it as I going from 1 to 2, j going from 1 to 2. These are bars, by the way, because they are midpoint. F of x I bar yj bar delta a. So you're writing this as a Riemann sum. That is the key idea behind it. And this is what the midpoint rule is for the double integral. So again, what is the midpoint rule? The midpoint rule is as follows. So if you have integral r going from integral of f of xy dA over rectangle r is same as summation I going from 1 to m, summation j going from 1 to n, f of xi bar yj bar delta a, where xi is the midpoint of xi minus 1 xi, this interval, and yj is midpoint of this. So I've just, the example we have done, if we generalize it, instead of having two divisions on each side for the intervals, if you have n and m divisions, this is what you get. And of course, when you take limit of this, you get the proper value of the integral, the right value. So that's why if you only do MNN approximation, then it's going to be approximate value. So this is the idea behind the midpoint rule of double integral. So again, how do we compute or calculate these double integrals? Of course, Riemann sum is one way out, but it's going to be pretty involving, right? So how do we go about? How do we find out these integrals? Okay, so that is what we want to do. Before that, I want to give you a few properties of this integral. This can be proved using the Riemann sum. Namely, if you take integral of f of xy plus g of, sorry, f of xy plus g of xy, it's same as taking integral of f of xy plus integral of g of xy over r. If you have c times f of xy, this is same as integral of c times f of xy is same as integral of c times the integral. And if f of xy is greater than or equal to g of xy, then you can say the same thing about the integral, that the integral of f of xy is also going to be greater than integral of g of xy. Of course, in all these we have the region R. In this lecture it's a rectangle, but it's true for general region as well, that these are satisfied. So again, coming back to thing, how do we calculate the double integrals? We want a mechanism to cover to calculate it. Riemann sum is all fine, but we want a easier way to calculate it. The way we did for we used antiderivatives for function of one variable. So we have the following result, which says the following: if you take a function f of xy, which is continuous on the rectangle a b cross cd, then integral r f of xy dA is same as integral a to b of, first you compute this integral, which is c to d f of xy dy, and then integrate the remaining with a to b dx, or c to d of a to b f of xy dx dy. So first of all, what are these integrals below? So first, this thing is called iterated integral. So c to d f of xy dy is called iterated integral. So we have this integral now, c to d f of xy dy. Let's call this as a of y, and let's call a to b f of xy dx as ax. So the idea is as follows. So what you want to do is you want to compute this integral. Then what you do is you integrate c to d f of xy dy first, this part here. So what does it mean? It means you're integrating f of xy with respect to y. So x is treated as constant. So you compute ay. So now you compute ay, which is, so let's call this as, actually it makes more sense to call this as, after the integral is done, it makes sense to call this as ax instead of ay. So let's call this as ax, right? Because after the integral is done, there's no more y, right? Because after integrating with respect to y, the remaining would be function of x. Yeah, let me show you that by an example. Suppose I have 1 to 2 of x, y, dy. So if I do this, x is a constant, it comes out integral 1 to 2 of y dy, you get x times y squared by 2, 1 to 2, which is going to be x times 2 squared minus 1, which is 3 by 2. And now if you look at this, this is actually a function of x, right? So it makes sense to call this as ax. So we take integral c to d f of xy dy, that is ax. Again, here we have x is treated as constant. Similarly, we have integral a to b f of xy dx equals to ay. So then the way to compute that integral is either you compute with respect to y first and then with respect to x, or you compute with respect to x first and then we compute with respect to y. So these two integrals are exactly the same. So these are called iterated integrals. Iterated integrals, the name means it's iterated, right? That you first do with respect to y and then do with respect to x. So you're iterating the integral. So if you think about it, you basically are, so suppose you're doing ax first. So suppose you're going this part. So first you compute ax, which is this area, ax, and then you keep, when you take integral from a to b of this, you're adding all the corresponding ax up, right? And therefore you get the total volume of this object. And similarly, it works for ay. So the fact that these two are equal, that c to d of f of xy dy then dx, and or you do a to b f of xy dx and then dy c to d. Note that dy, the limits of integration are c to d, right? So for y is changing between c to d. So and then the outer one x is changing with respect to what? With respect to, so the outer one x is changing from a to b. So similarly here, so equality of these two integrals in general would be discussed, but this is called Fibini's theorem. It's a very powerful theorem in the sense that it tells you that these two iterated integrals are equal, so you don't have to worry about which way to compute first. All right. So this gives us a power to compute the integrals now. Let's see this example. So we have 2 to 4 minus 1 to 1 of x squared plus y squared dx dy. So we will do the first integral. We'll do the first integral with respect to x first. So this is going to be x squared. So what is integration? Now we are integrating with respect to x. So integration of x squared will become x cubed by 3. Integration of y squared with respect to x, so you'll have extra multiplication by x, right? So the limits of integration are minus 1 to 1, and then you have, of course, the outside integral with respect to y. And then we look at this becomes, we have x cubed by 3, so we have 1 by 3 plus y squared, then minus of minus 1 by 3 minus y squared, integral 2 to 4 of dy. So in the end, we get 1 by 3 minus of minus, so 2 by 3, your y square minus of minus plus, so 2 y square 2 to 4. And that will be 2 by 3y plus 2y cubed by 3, 2 to 4. And then we basically are going to compute this. So you have 2 by 3, 4 minus 2 plus 2 by 3, 4 cube minus 2 cube. And what was the answer is the answer. However, note the following. Once this double integral is done, the output should be a value. Okay. So this theorem, so again, this Fibini's theorem is very powerful. It helps you to be able to compute the volume, or actually in this case, it's not really volume. It helps you to compute this double integral. Now let's look at the following problem. So we have integral of x sine x plus y dA. So we have, again, we need to write it as iterated integral. So we write it as, So let's choose which one to go first, either with respect to x or with respect to y. Now, I will choose to do with respect to y first because I have x sine. So I will have to use by parts, right? So let's take 0 to, so pi by 3, 0 to pi by 3 of, so this is what y is changing from. So sine x plus y dy, and then my x is changing from 0 to pi by 6 dx. So I'm writing this as now iterated integral. So now what is integration? So x is a constant with respect to y, so it comes out. What is integration of sine? Integration of sine is minus cosine of x plus y, right? Because integration of sine a x plus a dx is simply minus cos of x plus a dx, x plus a, right? So I'm using that here. Instead of a, I have what? Instead of a, I have x. So let me change this so that there's no spot for confusion. Integration of y plus a dy is equal to minus cosine of y plus a, right? So same thing here as well. Here x is a constant, right? And then the limits of integration are 0 to pi by 3, and then we have integral dx. Now this limit of integration is for y, so if you want you can write it as y going from 0 this. Now let's see, so we get 0 to pi by 6 minus x cos of x plus, so x plus pi by 3 minus of minus, so minus of minus makes it plus, plus x times cos of x dx. So now we want to integrate them separately. So now this is a integration of function of one variable. So we have to use integration by parts. So either we can do that way or we can combine them together because now we are doing one variable. So we have x times cos x minus cos of x plus pi by 3 dx. So in this case, this will be my u, this will be my dv, and then you can continue and integrate. So now this is the integration of function of one variable. So this is going to be x plus sine of pi by 3 minus cos of x plus pi by 3 for the first part, and for x cos x we get plus x sine x plus cos x, and you put limits from 0 to pi by 6, and the answer turns out to be pi by 2 minus 2 times 3 to the power 3 by 2 plus 6 divided by 12, but not pi by 2, so pi minus this. So this is how you would compute the integral. So now let's basically do this problem. Evaluate the volume of the solid that lies above the region, which is a square 0, 2 cross 0, 2 and below the elliptic paraboloid. So again, this basically 0, 2 to 0, 2 of z, which is 16 minus x square minus 2y square dA will give R. So if you're writing this way, we should write R. This is the volume. we don't write x 02 to 02 until we decide which one to integrate first. So now by Fubini's theorem, this can be written as 02, 02. We can decide now which one to go first. So let's take dx first and then dy. We will compute this integral. Again, the reason for this is Fubini's theorem. Fubini's theorem comes to rescue us here, makes computation easy. So we have 02. Again, so we have 16 integrating with respect to x. So 16x minus x cubed by 3 minus 2 y square times x 0 to 2 dy. So when we put now 0 to 2, so 16x. So 16 times 2 is going to be 32 minus 2 cube, which is 8 by 3 minus 2 y square times, so this is going to be 4y square, and then when you put 0 you get all 0, so dy. This is going to be 32 y minus 8 by 3 y minus 4 by 3 y cube 0 to 2, and again we have 32 times 2 minus 8 by 3 times 2 minus 4 by 3 times 8, and whatever is the answer is the answer. So you can simplify it if you wish. This is going to be 64 minus 16, so 16 minus 32, so minus 16 by 3, so 16 minus 32, so that's going to be 8, and then this is going to be, so that is going to be 192 minus 48 by 3, which is going to be 144 by 3, and that is going to be, so this is going to be 12 times 4, which is 48. So this is the answer. All right. Okay, so now let's evaluate this here. Integral of r xy square over x square plus 1 dA. Now, thanks to Fubini's theorem, this can be broken now into, so let's see which one to integrate first. It wouldn't matter. So 0 to 1. In that case, we are going with respect to x first. Let's go with respect to y first. It looks simpler that way. First, let's get rid of y. Fubini's theorem guarantees that it wouldn't matter what order you do the integration. So we have y going from minus 3 to 3 of x y square upon x square plus 1, 0 to 1 dy dx. So now this is going to be 0 to 1. Take x upon x square plus 1 common. You can do minus 3 to 3 of y square dy, and then whatever you get, you have to do dx of that. So in this case, y is a, so inside part is a even function, so you can break it as 0 to 1 x upon x square plus 1. Here you will have 0 to, so 2 times 0 to 3 y square dy, and then you do whatever you get, you do the dx of the whole thing. So you see there is some kind of a separation happening of y and x separately. So let's see, so we get 2. This integration is going to be y cubed by 3, 0 to 3. We have 0 to 1 x over x square plus 1 dx. So this is going to be 2. Y cubed by 3 is going to be 27 by 3, which is going to be 9. So that can come out. Integration of 0 to 1 x upon x square plus 1 dx. So you see the derivative of top is on the bottom, so you can see right away that this is going to be, so this 2 can be combined with this guy, so we get 9 times ln of x square plus 1, 0 to 1, so you get 9 ln 2 minus ln 1. ln 1 is 0, so you get 9 ln 2. So this is how we can compute the integral. Now, interesting thing to notice is that the interesting result to notice is the following. If you can break your function into f of x g of y dA over region R, where R is a rectangle. Note that this is only true at the moment for rectangles. For later on, if the region is more general region, which we are going to study in the next section, we have to do something more than that. So if you're doing the integral over rectangle, this is as if, because the function is separable, fx gy, it's as if you're doing fx dx and then c gy dy. All right. So the reason for that is, first of all, you have, this is your Fubini's. So if you apply Fubini's theorem, so you get c to d fx gy dA, but you have dx dy. Now, if you integrate this with respect to x, so in that case, if we integrate this with respect to x, what do we get? This is same as c to d. Now out of this, gy can come common because there is no x there, times integral a to b fx dx dy. Now note that once this integral is done, it will be a constant because there's no y there, right? So you can bring this out. You have a to b fxy dx, and then for the other one you have c to d gy dy. So your double integral breaks into multiple of two integrals, single integrals, if your function is nice and your region is a rectangle. So we'll continue with this in the next lecture when we discuss about more general region. We'll generalize some of these results. Thank you for your attention.